Okay, so welcome everyone to Calculus, Math 360. And then the other name for it is MEC 903 because it's an NCCP course. So both of those codes are kind of interchangeable. So this is a sequel to a previous calculus course that everyone presumably took. So the setup here is that I'm in a classroom. I'm in North Bay with some students, and then of course I'll be teaching out-of-town students. I think everyone out of town is Confederation College. I think there's maybe 15 or 20 of them. Yeah, and for the people online, I'm just curious, at Confederation for all your online stuff for NCCP, is everyone using Zoom, or are there other classes that are still using the Adobe Connect? Because I don't want to use that. We're going to use Zoom because it's a lot more convenient. But I'm just curious what everyone else is doing. And while you're typing, today is going to be an introduction to the course. So we're going to go through the course outline, a PowerPoint, the section-specific information, and then we'll do maybe like a bit of a review on some previous calculus stuff, just so everyone kind of gets back into it. Okay. Okay, so everyone else is using Adobe Connect. Okay, maybe everyone, let's see. So many emails. Okay. So hopefully everyone saw my email about Zoom. If not, I'll send another one, but for now, we'll continue with this. Okay, so let's start. Let's see, share screen. Let's go to, this is a welcome presentation. And if anyone online can't see the share screen or can't hear me, of course, feel free to jump in, even with your microphone, that's fine. Okay, let me just set up my writing utensil. Everyone just bear with me. Here we go. And I have a fancy writing thing that lets me write on the actual screen, which is cool and pretty essential for calculus. Okay, so let's jump in. So who am I? My name's John Heindel. I have an honors degree in math and business, and then I have a Master of Science degree in a thing called topology. And my office, I guess this office is irrelevant because that's the other campus. So everyone can reach me by email, and I'll always try to answer like at the very most within 24 hours, usually within a couple of hours. Unless I fall asleep for like 5 hours in the afternoon, which happens. In that case, you'll have to wait 5 hours. But typically I'm pretty good with answering emails. Here's a picture of me for everyone online. Okay, so Tuesdays and Thursdays, 9:30 for 2 hours each. So yeah, like I said, combination of in person and on Zoom. And for the North Bay people, do you guys think you're going to want to come in physically for class? Okay, that's what I prefer, just because like why not? We haven't done it in so long, so we'll come in physically. There might be some days where I might do it online, like if my car breaks down or something, or if it was the winter and it was really bad weather, we would do it online or something like that. But for the most part, we'll do it in class. Okay, so, and we'll be using Brightspace. Brightspace is basically like iLearn, except it's kind of used for the NCCP courses. And you guys all have your Brightspace logins, is that the case? Oh, okay, okay. Oh, but at least you still got my emails because yeah, okay, so that's good. Darn it, okay, so I'll have to, do you guys know who you would email about that? Otherwise, I'll have to. Can you talk to him again and see what he says? Do you guys have access to the iLearn at least? Okay, so iLearn, the North Bay students have access to iLearn, so I'll post everything on there as well, just so you guys have the material for now. So we'll do that. So it'll be both on Brightspace for everyone else and iLearn for you guys. And then we'll try to get everything on Brightspace. So that has all the lessons. That's where I'll post assignments and then attendance and grades and, all the usual stuff. So that is what we'll use for that. Let's see, and try to check like the Brightspace news every couple times a week. Okay, so here's the breakdown for the course. It's a pretty good breakdown. Like there's 10% participation, which is a really easy 10%, because like originally I didn't know how to figure that out because it's a partially online course. So I'm like, how the heck do you do participation with an online course? So for participation, what we'll do is after a lesson, I'll give everyone like 1 or 2 questions from the textbook, and everyone just has to try them and hand them in, and then we'll take them up the next lesson, and that's your 10% participation. So we usually do like 10 of those. So you don't even have to get the right answer, you just have to make a genuine effort to try the question. So it's basically a free 10%, and it's just free extra practice questions for us to do. So that's how the participation will work. And of course, for everyone online, for each participation, I'll just activate a Dropbox and then just take pictures of your answers or scan your answers if you can and just submit them on Dropbox. And yeah, we'll do it that way. Okay, and then 35% homework assignments. I don't know why it says homework assignments. It should just say assignments. So 35% is assignments, and usually we'll have a couple per chapter. Those are more formal. So typically I'll post that as a PDF online, and then you could, or I'll print it out for you guys, and then everyone just submit it on Dropbox, or you guys can hand it in person. Yeah, so those will be a bit bigger than the participation little quizzes. What else? Okay. And then 20% tests, really only 20% tests? Okay, that's actually pretty good. So 20% tests, typically we'll do a chapter, have a test, do a chapter, have a test. So it's pretty simple that way. And then 35% is the final exam. And to be honest, for the final exam, I don't bother covering everything. I basically just treat it as a last test because I just don't like covering everything at the end of the course. So it's called a final exam, but it's pretty much just a last test. Okay, and then there is the section specific information that's also posted online. We'll take a look at that in a minute. And that contains like a week-by-week breakdown of the course. That'll change, that always changes, but I guess it'll be roughly accurate. Okay, let's see what else we have. So only 3 chapters, but some of them are a bit long. So we got methods of integration, which is kind of fun. It's like 8 different methods of integration. It's not too bad. Then we have expansion of functions and series, which is also interesting, and then differential equations. And I'll also spend some time talking about like the history of calculus, usually just because sometimes just for fun, we'll talk about the history of calculus because there's like a lot of funny, interesting things in there. Like 2 people invented calculus at the same time, and they had like a giant kerfuffle about it, and it was a huge embarrassment, and it's like one of the most embarrassing things in the history of math, and they were like publicly sniping each other and publishing articles about each other. So it's a very fascinating history. Here's the textbook. Hopefully everyone at Confederation has access to it. To be honest, I don't have any context there. I don't know how to make sure that everyone has the textbook. So if anyone has trouble getting it, let me know. For the North Bay students, like I mentioned, I have physical copies that you guys can have. And everyone needs a standard scientific calculator. Yeah, you don't need like a graphing one or anything like that. I have a Casio calculator and I really like that. So yeah, just a standard one. And then here are all the expectations. Probably, probably the most important one is if you're going to miss a test, just let me know before the test, especially since things are really crazy this semester with trying to figure everything out. And we're going to have to figure out how to actually do the tests because I'm not aware if there's so many things I don't know this semester. It's very disconcerting. Hold on, I'm just going to go back to the Zoom. Stop sharing. Yeah, for people online, have you been informed if your tests will be supervised by a proctor, or has there been no discussion about that? I'm just trying to figure out what we're doing. Because if I do it in person with my North Bay students and everyone else does it online, that's a bit unfair. So we're gonna have to have either everyone doing it in person supervised or everyone just doing it online. So we'll have to figure that out. Haven't heard anything. Okay, so if they're not gonna get proctors for the out of town students, what we'll probably do is everyone will just stay home for the tests. I'll email it to them or to everyone. Everyone will have 2 hours and then you'll just submit it on Dropbox. That seems like the easiest and fairest way to do it. Because if I do it in person with you guys, everyone else has it open book technically, or I guess we could do it in person, but everyone can have their laptops. I'll figure it out, yeah. But I think for now, the simplest thing is we'll just say that we'll do them online. But obviously we'll discuss that further when we get there. Yeah, previously they would have proctors for the out-of-town people, but I don't know if they're doing that because of the circumstances. And then here are my expectations. Attend class, of course, provide clear lessons, consistent evaluations, and then of course, communicating with everyone actively, especially since a lot of this is online. So that's just a basic introduction to the course. Again, does anyone have any tentative questions at this point? Everyone's good? Okay. Let's just take a quick look at the other documents. We did that one. Let's look at the course outline. I'm just gonna stop sharing and then reshare this. Okay. So here's the course outline. It offers kind of a point-by-point breakdown of everything that we're doing. Aside from that, it doesn't offer too much. I think it has the breakdown for the grades as well. So 35%, 20%, 10%, 35%, et cetera, et cetera. Here's the textbook that is listed. So that's good. That's basically it for the course outline. And then let's go to the section-specific information. So like I mentioned, it's a pretty good document because it has a week-by-week breakdown of everything that we're doing. So it looks like we have 5 weeks to do chapter 1. So that's pretty good. And then, yeah, the breakdown is pretty simple. And oh, another thing I have to mention is that for assignments, I'll typically post them early. Like usually I'll post them even before we cover material. And the reason is just it's so everyone can work on it as we're covering stuff. Plus, the main reason is I'll forget to post it if I don't post it early. That's really the reason. So yeah, if you see an assignment that's up and we haven't covered it yet, don't freak out. Plus on news, there will be a clarification that it's just posted early, just to have it up there. So that's why all the assignments are listed like right at the beginning of each chapter, but they won't be due obviously until later. So assignment test, blah, blah, blah. So we have expansion of functions in series, that's 3 weeks. And then that's like, what is that, 6 weeks for differential equations. So it's not too bad of a course. There's not too much material. Oh, one other thing is there is a late option. So you can hand your assignments in up to 3 days late, but you get a 10% penalty per day. And it's just easier for me. Then I don't have to evaluate if a person has a valid excuse or an invalid excuse. It's all just quantified. But just note that typically we'll take up the assignments, and if we take them up, then the late option is void. Like if we take it up the next day, then that's just the way it is. So it depends. Typically, you'll have that late option unless it's specified otherwise. Attendance, etc. Oh, and then there's the academic integrity thing. So the academic integrity policy is posted online. So everyone check that out. So in regard to that, it's good for people to work in groups and stuff like that. The only problem is when like 2 independent people hand in like completely carbon copy assignments of each other. And it's obvious that, yeah, so you can't do stuff like that. So like, let's say that you are working with a partner on your assignment and you're concerned that they might be too similar, just ask me about it and I'll look at them and I'll just tell you. Or just hand it in as a pair and just put both your names on it and let me know, and you could do that as well. So there's like a ton of options. You could hand them in as a group. So yeah, there you go. And that's basically just, oh, so, go ahead. I think we would just discuss it on a case by case basis. Yeah. In that case, if you guys were concerned they were too similar, I'd prefer that you show me like a bit early, just so I can let you know. Yeah. And the reason there's all those options, it's basically so that if people do copy off each other, they don't really have any excuse. So like I'm trying to provide as many opportunities for people to avoid getting in trouble. So handing in group assignments is fine, or partnered assignments is fine. Just let me know and just have all your names on it. Okay. And that goes for everyone online as well. Okay, so that is all the initial information that we have. So it's only 10 o'clock. So let's cover some stuff. We're not going to cover any new stuff, but I have some resources online, like some formula sheets that have just like differentials and integration formulas and stuff like that. So let's go through those. Okay, so chapter 28, methods of integration, resources. So this should be posted online. And again, I'll post it for everyone in North Bay as well. So I don't have a formal review of previous calculus stuff, because one time I tried and then I realized that it was an entire course, because it literally is an entire course that you guys took previously. So I don't have anything formal. So bear with me. I'm just going to kind of look at these and improvise to everyone, and hopefully my explanations will seem logical. So this is, oh, let me just resume share. Darn it. Hold on. Stop sharing. Share screen. And where is it? Here it is. Okay. Darn it. Okay. Get out of the way. Here we go. So yeah, this is just a formula sheet I found probably just on Google that shows a bunch of differential equations, and then it shows also a bunch of integration formulas. For now, you could basically kind of ignore the integration formulas, because a lot of those are what we'll be doing in this course, so don't worry too much about those. But it's good to just go through a review of differentials. And hold on, I'm going to go to a whiteboard. Let me just bring this up on my other laptop so I can see it as I'm whiteboarding it. Okay. So some differential formulas, new share whiteboard. Okay, so we'll go through a couple of formulas, and then I'm going to like do some graphs of some differentials, just so you can kind of see how to picture them and stuff like that. So here we go. The first formula we have is the derivative of, why is this blue? I want black. Okay, so first formula we have is that the derivative of x, so this is the format that there's various formats you can use, but here's kind of the format that we're using. Derivative of x equals to 1, or kind of a better format, you're free to use any of them, would be x like this equals 1. That's also a sign for derivatives. So that's the first formula. Basically, if you have a function x and you take the derivative, it ends up equaling 1. I'm just curious, do you guys remember what derivatives like visually represent or anything like that? Do you guys recall kind of what the purpose of those are? You're free to say no. There's no wrong answer. Okay, so let's do a couple of visual examples just so we know what we're talking about, because I realized the last course was last winter, so that was a while ago. Okay, so let me show another derivative, because this is the one I have a graph kind of prepared for in my brain. Let's see, derivative. So let's look at derivative of a constant. Sorry, I keep getting emails. Sorry, they're distracting me, sorry. Derivative of a constant is equal to 0. So what the heck does that mean? So let's draw a graph, and let's imagine like a practical scenario. Let's imagine that you are in a car. So let's look at like the distance you're going in this car compared to time. So I think we'll put distance right here on this axis. Distance, this is a terrible way of writing it, but whatever. And then time on this axis. So let's say that you took, in this case, we're just looking at a constant, which is just a thing that doesn't change. And let's say that was your distance in your car. So let's say your distance is right here. Here's your distance in your car. So as time is going on, your distance isn't changing. It's not going up, it's not going down. You're just sitting there in your car and you're not driving anywhere. It's just like you're at the same distance, et cetera, et cetera. So that's one scenario we can kind of picture. Now, in this case, a derivative would represent how fast the car is going. So in this case, since you're going 0 miles an hour, you're not even moving, the derivative in this case would be 0. So basically, if a function represents like the distance of a car, a derivative represents how fast that car is going. It's about rate of change. Or if you had a graph that showed how fast you were going in a car and you took the derivative of that, the derivative would then be the acceleration of the car. So it kind of just like you take the derivative of the distance, it turns into speed. You take the derivative of speed, it turns into acceleration. Is there anything after acceleration? I don't think so. I don't think there is. So that's what a derivative is. It's looking at how fast something is moving. So in this case, the graph for this derivative would just be a graph where you just have your value, your line at 0. It would just be constantly at 0 because the speed is just 0. You wouldn't be going anywhere. So I'm just drawing it so you can see it. So that's visually what a derivative represents. So it's always my advice to try to visualize stuff because that's how all the mathematicians kind of do it. And that's always how I try to understand calculus, is just to see it as a picture in my head. Let's look at a different one because derivatives are a bit tricky. Let me think of another one. Let's see. Well, let me look at this. So we have derivative of, here, we'll go through a couple of them. And if I find a good one for a graph, then we'll do that. And I'm just going to switch to a better notation. I'm just going to switch to this notation. So derivative of x is equal to 1. And I'd recommend memorizing these just because it's a thing that eventually just becomes like part of the language of calculus. Yeah, so derivative of x is equal to 1. If you have derivative of ax, that one is just equal to a. So that one's kind of easy to remember. You just keep the letter in front of it. And then if you have x to a power, let's say x to the n, and you take the derivative of that, in that case, the n kind of drops down in front of the x and becomes a number. And then you subtract 1 from the exponent. And that's the formula for x to the n, taking the derivative of that. That's one especially that you should memorize. And it's not too bad because, again, it's just like drop the n down and then subtract 1 from the exponent. And then there's a bunch of other ones. The next ones are some trig functions. But before we go to that, let's do another more basic visual graph of one of these. Let's do, hold on, let me clear this. Let's do this one. Let's just do the fact that the derivative of x is equal to 1. Let's just do that. So let's draw a graph of x and see what it looks like. Then let's draw a graph of its derivative and see why it's equal to 1. So the graph of x, so let's just do, so x, y. The graph of x would just look like, let me try to draw this. And just a warning, my drawings are always horrible because this pad is hard to use. Yeah, if you have a graph x, it just looks like this. It's just like a perfectly symmetric type thing. And like that, and just pretend that that's pretty good. Just pretend that it's like a straight line. So this is just x, or you could say formally as a function, it's y equals x. So if that was your original function, again, you could picture that it's a car, maybe it's the distance of a car. And in this case, you could see that the distance you're traveling is completely consistent. Like you're not going faster or slower, you are traveling in your little car, but it's just going very consistent. So that's why the derivative is just equal to 1, because your speed is just like same speed, same speed, same speed, same speed. You are going somewhere, you're just not accelerating. So that's why in this case, the derivative would just be, it would just be the line 1. It would literally just look like this. It would just be consistent speed. You're going maybe 1 mile an hour and you're holding up traffic, whatever it is. So hopefully that helps people at least picture what the heck a derivative is. It does have a physical meaning in reality. And again, it's just looking at how fast something is going. Do you guys have any questions about any of that or anything so far? Let's see, what else? What else would be what would be a fun graph to look at for derivatives before we move on to trig? Because everyone always dislikes trig. I hated trig in high school, but now I really like it. Okay, So those are derivatives. Okay, so let's move on to some trig derivatives. Maybe before that, we should just look at some basic trigonometry stuff. Because again, everyone, that's one of the things from high school that people are traumatized by is trig stuff. Okay, so the trigonometric functions are particular types of functions. Maybe for the first one, we'll look at sine. There is one thing that everyone remembers from high school, which was SOHCAHTOA. Remember that? Even I remember that. I remember SOHCAHTOA, and I remember y equals mx plus b, because I did not pay attention in high school. And yeah, so it's kind of surprising that I actually got a degree. Okay, so let's look at sine. So there's a bunch of trig functions. They're like these weird repeating oscillating functions. They're really cool because they appear in nature all the time. Like they appear in the study of music, and there's like a billion different applications in the textbook that we're going to look at in regard to like engineering and stuff like that. So there's a bunch of trig functions. There's sine. So let's just say sine x. There's cos, and there's tan. So those are the three main ones. So let's look at the graph of one of these. Let's look at the graph of sine. So again, just as a warning, they're a bit weird compared to other functions. Okay, so let me try to draw this, and let me try to remember what it looks like. I haven't done this course for like a year. Sine looks like this. Looks like that. Ooh, that's nice. And then it repeats, it keeps going and it repeats forever. Like keeps going like that, and then I'll just put etc. So it repeats, and then it also repeats on this side as well. And that's what it is. It's called a periodic function. And let me label, so it repeats every, so on this axis right here, you have either degrees or radians, like the angle that you're interested in. And then here you have the actual value. So here you would have 0 degrees, 90 degrees, 360 degrees, and then it just repeats every 360 degrees. It's like the equivalent of spinning in a circle, and you just repeat it. And then same thing on the other side, 0 degrees, 90 degrees, 360 degrees. Oh, 180, yeah, you're right, sorry about that. This should be 180, yes, exactly, thank you. Because 180 is halfway, yeah, exactly. Yes, 180, very good. So yeah, it goes 0, and then 180, 360, and then I think 90, yeah, 90 should have been right here. 90 would be obviously halfway between 0 and 180. So you got all these angles, and then you got various values, like at angle 0, you just got 0, that's right there. At angle 90, this is actually 1. And for the actual values, it goes up to 1 and then down to 2, or sorry, down to -1. But it doesn't go any further than that. So it's kind of just like stuck between those two values, and it just like bounces around between 1 and -1. So that's the sine function. I would also memorize this. I'm probably going to say that for everything, but it's just like for answering various questions, it's really useful to have the graph, because there are plenty of times where I either don't have my calculator or I'm too lazy to reach for it. And a lot of the times you could solve stuff just based on the graph, because it has like, you could see that 0 degrees is 0, because that's just right here. You could see that 90 degrees lines up with 1. So that tells you that sine of 90 degrees is equal to 1. So there's like various things you can deduce from the graph. Sine of 180 degrees is equal to 0, because that's just right here. Sine of 360 is equal to 0, et cetera, et cetera. So that's the sine function. What else can I say about that? And like I said, it has like a billion different applications. It even appears in nature and stuff like that. And then you have the cos function and the tan function. Should I draw the cos? I'll try to draw the cos. Let's draw that. Let's see. Cos x. So cos is kind of easy to draw because it's the same as sine, except it's just shifted over 90 degrees. So instead of starting at 0, it starts at 1, and then it goes like this, and then it just oscillates forever like that. So it's actually the same curve, it's just moved over a little bit. So this would be, let me just try to get this. So this would be 360. That's where it repeats. 180 would be halfway through, so that'd be 180. And then 90 would be here, 0 would be here, et cetera, et cetera. So again, the graph tells you like a couple of things. It tells you that cos of 0 degrees is equal to 0. That's just referring to this value right here. Cos of 90 is equal to 0. Cos of 180 is all the way at the bottom, so that would be equal to -1, because again, it goes down to -1. And then for 360 degrees, it's all the way up here, so cos of 360 is equal to 1, et cetera, et cetera. So basically, the point of cos and sine is that you plug in an angle and you get a number, and it'll give you a number between 1 and -1. So it's pretty limited in terms of what it can actually take in and what answer it actually gives you. What else? So this is one way of setting up the cos, the trigonometric graphs, is you could use degrees. Most people are used to degrees because they know how they work. But more commonly, we'll use something called radians. Have you guys heard of? Okay, so you at least covered it in the previous. Okay, so let me redraw this with radians. So radians are like degrees. Degrees go from 0 degrees to 360. Radians are similar, except they're not actual degrees. They go from 0 radians to 2 pi radians. So basically, yeah, basically you do one full rotation in degrees, it's 360 degrees. If you do one full rotation in radians, it's 2 pi radians. And the reason they use 2 pi is because if you have a circle and the radius is equal to 1, the circumference, like the length around the circle, is 2 pi radius. So that's kind of where that comes from, where going around a circle is 360 degrees, and going around a circle in terms of length is 2 pi times the radius. So they were like, hey, let's just use radians, and we'll just say that 2 pi radians is one full rotation. And then it actually kind of has more logic than 360 degrees, because it's like, for 360 degrees, what logic is there for that? Like when you really think about it, it's like, why is one rotation 360 degrees? Why isn't it like anything else? I think the reason is probably because there's 365 days in a year. Another reason might be because the Babylonians had a different number system, and they had like a lot of 360s in there because it was all based on 60. So it comes from places, but degrees to me don't make sense. Radians actually make a lot more sense. So for the graph, if you were to replace the degrees with radians, it would be 0, 180 would be pi radians, 360 would be 2 pi radians, 90 degrees would be, that's halfway, so that would be pi over 2. So you could either use degrees or radians. They're the same thing. People don't like radians just because they're not used to them. But if anyone has trouble with them, we can go into them in more detail kind of later on. But yeah, basically at this point, it's just 360 degrees is a full rotation, and 2 pi radians is also a full rotation. Yeah, a degree is like a little slice because you need a lot of them to go in a full rotation. A radian is like a larger chunk than a degree. You only need roughly 6 radians to go around a full circle. I say roughly 6 because 2 pi is roughly 6. It's what's 2 pi? It's 6 point something. Sorry? Yes, exactly. Yeah, because 1 pi is 3.14. So yeah, exactly 6.28. So yeah, it's like roughly, so radians would be like kind of like these big chunks around the circle, and there'd be roughly 1, 2, 3, 4, 5. You know what I mean? I'm bad at drawing these things, but yeah, roughly 6 of them. More exactly, 2 pi of them. Geez, so much stuff. I realize this is overwhelming, but again, I can't teach an entire course of review, so we got to just kind of just gloss over some things and just do our best. So those are the trig functions. What else? What else can I say about those? And there's another cool thing, which is the special triangles. Let's get rid of this and let's look at those. So let's say you're trying to figure out a particular angle for sine. let's say someone asks you, what the heck is sine of 25 degrees? Now for that type of thing, for 25 degrees, it's not like sine of 25 degrees is common. So you got to just use a calculator. You got to just type in sine 25 degrees and it'll give you your answer. But there are other ones that are easier to figure out and you don't need a calculator for them, which is super cool. So the way you figure these out is something called special triangles, which are these particular triangles that you can memorize. And then you can do like all these tricks to deduce various trig angles from them. So let's look at the first, and this is all online. So let's see, special triangles. I remember these from high school, and when I understood them, I was like, man, these are badass. Let's look at the easiest one, at least the easiest one to memorize. Oh, and before we do that, we should also look at, let's write down the basic definitions of sine and cos and tan. I probably should have done that earlier. So sine, so this is where SOHCAHTOA comes in. SOHCAHTOA. And this is a little memory device for remembering the definition of sine and cos and tan. So where sine and cos and tan come from is that you have a right triangle that I am trying to draw. Okay, so a right triangle. Here's a right angle right there. And then basically you pick an angle, or an angle will be specified to you, let's say right here. And then sine and cos and tan is basically a ratio between the various sides of a triangle in regard to that angle. So for example, sine of this particular angle, I'm just using the symbol theta because it's commonly used for angles. Sine of theta is, you just look at SOHCAHTOA, and it is opposite over hypotenuse. So in this case, your theta is here, your opposite side is opposite to theta. You have something called the hypotenuse, which is always this side right here, opposite the 90-degree angle. And then whatever side that theta is touching is the adjacent side, or at least the side that it's touching that isn't the hypotenuse. So that's basically the setup for sine and cos and tan. Basically, you have a triangle, you have an angle, you have all these sides labeled, and then sine and cos and tan are various ratios of these sides. So sine, if you look at SOHCAHTOA, is opposite over hypotenuse. So sine is opposite over hypotenuse. So basically what it means is that sine of theta is whatever this is divided by whatever this is. That's technically the definition of sine and cos and tan. Seems like kind of arbitrary definitions, but again, they're very useful functions. So that's why SOHCAHTOA is great, because it makes it really easy to remember. And then cos is, so cos is CAH, so that's adjacent over hypotenuse. So if you had the cos of this angle, it would be this divided by this, and then et cetera, et cetera. Tan is TOA, so tan is, tan of theta is opposite over adjacent. So those are the definitions of the three basic trig functions. But thankfully, all you need is SOHCAHTOA, and you could at least deduce all of this just from that. So sine, cos, tan, good. What was I doing before this? Oh yeah, special triangles, super awesome. First one is this one. So this is another, so it's a particular triangle. So here's 90 degrees, and basically you have 45 degrees here, 45 degrees here. And the reason I know this is it's just memorized. And then 1 and 1 and square root 2. So this is a very common, again, special triangle, and this can allow you to deduce various angles. So let's say that someone was asking you, what the heck is sine of 45 degrees? Maybe you're on a game show and you're about to win a bunch of money and you don't have a calculator. Obviously, you could just use a calculator, but again, we're going to pretend that you don't have a calculator. So in this case, it's like, well, how the heck would I figure out sine of 45 degrees without a calculator? I'm at a loss. I'm going to lose this car that I'm about to win in this game show. Not to fear. All you do is look at, so sine is opposite over hypotenuse. Let's write that again. And then all you do is you look at this special triangle, pick one of the 45-degree angles, it doesn't matter. Here we go, pick that one. And then you just look at the opposite of that one. Opposite is 1. So let's put 1 there. And then hypotenuse is square root 2. So you've just deduced that sine of 45 degrees is 1 over square root 2. And all you needed was just this pre-memorized triangle and SOHCAHTOA. And you could technically deduce a bunch of different stuff. You could do the same thing with cos. Cos would be, let's see. So cos of 45 degrees. For cos, of course, you have to use adjacent over hypotenuse. So that would be adjacent is this, and hypotenuse is this. So that's 1 over square root 2. So that happens to be the same as sine. And then you could use the same thing for tan. So they're really cool in the sense that they can allow you to deduce like the basic angles without a calculator. So I guess you don't have to memorize this because like these are all online and I'll print them off for you, but they're really, really, really cool. And then there's another one that's also super cool that has a bunch of other angles. Let's see. So this one I can never ever memorize. So I always just have to check my notes. So 90 degrees, 60 degrees is on top right here. 30 degrees is right here. And then the sides are 1, square root 3, 2. So this one's also useful because you can deduce the sine of 30 degrees, the cos of 30 degrees, the tan of 30 degrees, the sine of 60 degrees, the cos of 60, like all these. So you could do 30 degrees, you could do 60 degrees. So all these, the most basic of the angles. So again, if someone asks you what the heck is sine of 60 degrees and you don't have your calculator, you go to SOHCAHTOA, SOHCAHTOA. Sine is opposite over hypotenuse. So you kind of set that up. And then since you're interested in 60 degrees, you circle that one. And then you just look at what's the opposite of 60 degrees. It's this. So we'll put that on top, square root 3. And then what's the hypotenuse? It's this right here. So square root 3 over 2. So, so there you go. And it's pretty cool because like the answer is an irrational number. So you've just deduced an answer that would normally be pretty hard to deduce, but you've done it just kind of using these couple basic tools. But again, you could always just use a calculator. So maybe all of this is academic, but I really like these triangles because sometimes they can save time. Questions so far? Again, I realize this is a lot of stuff. Okay, so we've done some basic trig stuff. Now let's go through this part's not too bad. Let's go through the derivatives of the trig functions. So does anyone remember what the derivative of sine is? Anyone? It's even I forget it. What is it? Oh yeah, it's cos. So that's pretty easy to remember. Yeah, derivative of sine is cos. They're all kind of connected with each other like that. And then the other one, derivative of cos, is actually equal to minus sine. So you got to kind of just remember that. I always have to repeat it in my head. I always think, okay, derivative of sine is cos, derivative of cos is negative sine, and then I at least don't get them confused. And what else? What other derivatives are there? I should move this closer. There is, so sine, cos, tan. Derivative of tan is, let's see, derivative of tan is secant squared x, which is another trig function. So on the formula sheet, all these derivatives of these trig functions are listed. So try to look at them. And yeah, maybe I'll bring up the actual, yeah, darn it. Let's see. Where's the actual, here it is. So here's the actual sheet right here. So derivative of cos is minus sine. derivative of sine is cos, derivative of tan is secant squared x. And then you got the other more advanced trig functions like cotangent and secant. So you got those derivatives right here. Those are a bit hard to memorize. I think I kind of have them memorized, but I have to like rememorize them every semester. But again, everything's included here. I'm just trying to think of what else we should cover before we, I'm thinking of, yeah, let me think for a second. So let's look at some of these integration formulas now, and then we'll look at some more advanced ones in the actual course. That's the bulk of the course, is looking at integration formulas. So basically, there's various ways of thinking about what integration is. Probably the easiest but most basic way is to think of integration as being the opposite of derivatives. If you take a derivative of something, it kind of takes you in one direction. And then if you were to take the integral of that, it would return you to what you originally had. So it's like, what would be a good analogy? It's like plus and minus. It's like forward and backward. Yeah, derivative and integration, they kind of cancel each other out. And let me go back to, I'm sorry, I keep switching things, but I like to be able to physically write stuff. Like here's one example. Derivative of x is equal to 1. But you could also kind of reverse that. So for example, if you took the integral of 1, it would return you back to x. So you could almost think of an integral as an antiderivative. It just cancels it out, which is really interesting because most people don't know this, but integrals were actually invented first before derivatives. That's interesting because like when we teach it, I agree with the way that they teach it, teaching it in the context that an integral is an antiderivative. It's easier to understand, but I just find it fascinating that derivatives, they didn't even exist at the time that integrals were invented. So they invented integrals, and then eventually someone called Isaac Newton, who was a physicist and mathematician, he invented calculus. He eventually discovered the fundamental theorem of calculus, which basically revealed that a integration is just an antiderivative. It's just reversing a derivative. So it's just kind of interesting that the way that we present things in the classroom, it's like after hundreds and hundreds of years of like organizing stuff. But when they originally invented it, it was like all over the place. And yeah, so that's integrals. Again, that's one way of thinking of them. Another way of thinking of them is that the integral of a function is telling you what the area underneath that function is. So if you had, I'm just going to say, let's just be really lazy and let's just do integral of function. And the function will be called function. And let's say that you drew a graph of this function. And let's just say it's some ugly something like this. The integral just represents all the area underneath your curve. That's what it kind of visually represents. So that's the original invention was for that purpose, was like, what are areas under curves? And Isaac Newton invented integrals, and then that kind of blew calculus up and blew engineering up, and was very beneficial to the human race. So those are integrals. So we'll do a couple more of those formulas just to kind of reiterate the connection between them. Let's see. So there's other stuff like, here's another kind of easy one. Derivative of sine is equal to cos. So if you took the integral of cos, it would just revert you back to sine. Yeah, and et cetera, et cetera. So again, most of the course is going through these integrals. So we'll definitely do them in more detail. But for now, I just want to illustrate that there's this logical connection between integrals and derivatives. One reverses the other. What else? What else? Anything interesting here? Okay, so I think we've exhausted this particular formula sheet because everything else is stuff that we're going to like actually cover. So I'm going to look at, let's see what else we have. we have this. Okay, so I'm just looking at the chapter 28 formula sheet because that also has some useful stuff. There's also something called trigonometric identities, which are various trig formulas that can be used in various circumstances. So again, these are all online. You don't have to necessarily memorize them, but let's look at a couple of them. First one is a really, really common one, that if you take the cos squared of an angle plus if you take the sine squared of an angle, it equals to 1. So that's a nice little neat formula. Yeah, and it's pretty easy to memorize. And then there's other ones, like if you take 1 and you add it to tan squared x, that equals secant squared x. And then there's a bunch of other ones. Again, you don't have to memorize them, but at least kind of look over the formula sheet and be aware of them because we'll be using them in later chapters. And then there's other ones like 1 plus cotangent x is equal to cosecant squared x. Yeah. And some of these there's like little tricks for memorizing these, like tan and secant, they always seem to be connected. And then cotangent and cosecant also always seem to be connected, because tan is connected because its derivative is secant squared x. So for some reason, those are always paired together. Cotangent and cosecant are always like paired together in various formulas. So I find that that's how I remember these, or try to remember these. Okay, so, and then there's about 3 other identities. But again, I don't want to this is just kind of empirical information. Here's kind of a neat one. If you have sine of 2x. So yeah, having like something like sine of 2x kind of sucks because usually you just have sine of x. So a lot of the times it's like, why is there a 2x in there? How the heck do I manage that? Well, there's a nice identity that sine of 2x is equal to 2 sine x cos x. So that's actually really nice because you have a 2x inside of your function, but when you use this identity, now you just have like normal sine x and normal cos x. So these identities kind of allow you to like wriggle out of trouble in some cases where you have something that you don't want to deal with. Okay. So that was a lot of little review. Oh, and also there are some chapters I recommend for review in case anyone wants to take a look at them in the textbook. Let me just, I think they are listed at the end of the first PowerPoint. Yes, so it says, if you need a review on derivatives and integrals, check out chapters 23, 25, and 27. So those are like the bare minimum ones I recommend. Okay. Any questions, any topics anyone wants to cover, or any topics anyone was confused about previously? Or man, it's so weird being in a classroom with actual people. Like I'm so used to teaching alone. It's actually really, really nice not teaching alone. It's the most awkward thing in the world, explaining calculus to no one. At least I have my bunny rabbits. They're sitting there with me, but like and my pythons. But no people are there. I'm just going to check on the people online. And I should probably, do I take attendance for this course? I don't think I ever bothered taking attendance. I shouldn't say that out loud. So how is everyone online doing? So we have a bit more people, thankfully. Does anyone online have any questions, or did they miss anything? We kind of went through the logistics of the course, and then we of course went through some more technical stuff. I guess everyone online is good. Okay, give me another minute to try to figure out if we should start on some actual material or if we should just call it a day. Let's see. let's do a couple more things. Okay. Questions, guys? Okay. So here is another, here, I'll bring this up. New share. Let's see. Where is it? Just give me a second, sorry. Cancel that. Guys, do me a favor, just try not to chat as we're doing the lesson. I have nothing against it, it's just like it just distracts me. What's that? Okay. Let's see. Oh, and speaking of, I just mentioned my animals. I'll try to bring in some of my animals for you guys. I got, and for everyone online, I'll try to do like a from home class so I could show everyone all of them. So I got some snakes, I got some bunny rabbits. They don't get along very well. That's a joke, by the way. I don't let them interact. They're pythons. But to be honest, I think my bunny rabbits could probably take on my pythons because my pythons are a bunch of little, what's a not horrible word to you? They're very timid. They're extremely timid. Like I feed them mice and they're afraid of the mice, and the mice are dead. Like pythons are such little babies. The other day, I let my python out. I took my eyes off of it for 5 seconds, and then I could not find it for an hour. And I found it on top of my dresser, hidden inside of a Kleenex box. And it's a 3-foot python, and it was inside of a half-full Kleenex box. And it's still in there 3 days later. It loves its Kleenex box. It's so funny. Yeah, and I got a bearded dragon, which is it's about a lot of people know about bearded dragons. I'll bring him in because he loves traveling, and I'll put him on my shirt, and I'll just like walk around with him all day, and I'll drive with him, and he just like hangs on my shirt for like 10 hours. He's so cool. He just like likes to chill with everyone. I'm getting distracted. Sorry about that. That's a habit I developed from doing too many online courses alone. Okay, so this right here is another thing. And online, this is just all listed under resources. So this is, for example, we have sine and we have cos and we have tan. And then we have these fancier ones called cosecant, secant, and cotangent, which are basically just the upside down of each of sine and cos and tan. So as you can see here, sine is just 1 divided by cosecant theta. So if sine was equal to, let me think of so whatever sine is equal to, cosecant is equal to just 1 divided by whatever that is. So they're always just flipped upside down. So yeah, if cos was 1, then secant would just be 1 divided by 1. It's just whatever happens to be. And then yeah, so sine is equal to 1 over cosecant, cosecant is equal to 1 over secant, and tan is equal to 1 over cotangent. So just try to remember that however you can. Yeah, it's kind of hard to memorize because it just seems like random words that they used. There's no like visual logic to it, but try to memorize those. So when I'm talking about like cosecant and secant and cotangent, that's what I'm referring to. They're just like the upside down versions of sine and cos and tan. And then there's a bunch of other fancy identities. There's a lot of them. Yeah. These ones are useful as well. So here are some even odd identities. So it says that sine of a negative angle is just equal to negative sine. So basically what that means is that sine has like this symmetry, and that's just due to the fact that it repeats over and over again. Yeah, and then for cos, you actually get cos of negative theta is just equal to cos of theta. So again, that's just due to its symmetry. Actually, for that particular one, let's draw just that one, just so we can see the logic that's going on. Okay, cos. So it just said cos of negative theta equals cos of theta. So I never like to take anyone's word for it. I always like to draw it myself or prove it myself just so it seems reasonable. So cos looks like this. I'm not going to draw the whole thing. I guess that's kind of a joke because it goes on literally forever. So of course you can't draw the whole thing. Here, I'll just draw both these. So it's basically saying that if you take, let's say, cos of a negative angle, so this is the positive side right here, this is the negative side to the left. If you take cos of a negative angle, let's say right here, then it's going to give you the same value as cos of that positive angle. If I actually drew it properly, it should be like symmetric and look proper. I'm just a bad drawer. But yeah, it just means that anything you plug in on the left side is the same value that you'd get on the right side because they're literally just the same thing going rightward and leftward. So little things like that. But yeah, it's always my advice is draw whatever you can, just so you kind of convince yourself of the logic that they're presenting. I think that's all we'll do for today. And again, I realize that this is kind of like a lot of stuff and all over the place. And I tried previously to do reviews, but then it was like prepping an extra course, and we just don't have time to do an extra course. So check out those chapters in the textbook. And then next time we will start on some of the actual material, which isn't too bad. It's just going one by one through various integration formulas. So we'll present one particular formula, and then we'll do at least like 5 or 6 examples, and then we'll go to the next one. Okay, let's stop sharing. Someone just asking, is today the first official day of class? I thought it was tomorrow. Today is the first official day. Monday was Monday a holiday yesterday? Okay, yeah, Monday was a holiday. Today is the official start of classes. Okay, no one, okay, so we haven't used it here. I see. So even everyone at Confed is having trouble with Brightspace as well. So I'll have to send emails about that. I wish I knew. I'll figure that out. For now, what I'll do is, this is a tough one. Today, just as a Band-Aid, I'll email everyone the essential material. And then I'll, for the North Bay people, I'll put it on iLearn, and then I'll try to figure out the Brightspace stuff as well. And if you guys have any contacts on your end for Brightspace, please reach out to them and let them know, just because I don't have any contacts at any of the other colleges. So just try your best to speak to your administration about that. Okay. I'm trying to think of any other way everyone can access these things. I guess I could post them on my Facebook. I don't know. What's up? Yeah. Okay. Let's see. Let's just try to find it through Google, and we'll see if we could do that. Okay, so one of my in-class students just mentioned that they can't even really find Brightspace to even log in, but let's just, I'm just gonna try to see if I could find it via Google, and then I'll show everyone else how to find it. I'm just gonna type in Brightspace NCCP. It looks like that didn't work. Let's try Brightspace. Let's just, Okay, let's just go to what I have in my history and all. Okay, login, let's see. So everyone just give me a minute to try to. So no one was even sent a link to Brightspace? Okay. That's it. People are always, okay, so it seems that things are a bit unorganized this semester. Let's see, Brightspace. Okay, let me, so I just found, let's see, so yeah, Northern Colleges collaboration, NCCP, Brightspace. Let me try to find it on this computer so I can, darn it. Okay, what did you type in? How did you find it exactly? Oh, okay, so let me try that. NCCP, Brightspace. Okay, perfect, perfect. Yeah, so for everyone, if you go on Google and you type in NCCP Brightspace, like this, it'll be the first result. So a page will come up and it'll say Northern Colleges collaboration, and then it'll have a list of colleges on the right side, and then you just click your appropriate college. So that's what we'll try for now. So it says Cambridge College, Canada College, College Boreal Confederation, Northern, and Sioux College. So everyone type that into Google, NCCP, Brightspace, click on your appropriate college. I believe that your login, what's your login, guys? Okay. Is it the same as for iLearn? Mm. Yeah, that's true, yeah. Okay, so it looks like people are finding that, and my North Bay students are telling me that it's basically the same password as what they use for iLearn or self-service. So everyone at KidFed, try that. NCCP, Brightspace, go on Google, find first result, click your college. I think that if you haven't set up a password, I think that the username is just your student number, and the password is just like your date of birth. It's something basic like that. But I'll send an email about this regardless. But at least we have a couple of people who have logged on. So you guys will be fine for Brightspace, it seems, for the North Bay students. So I won't bother posting anything on iLearn. I'll just stick with Brightspace because that's the one that everyone's going to be using. Yes, yeah, that's true. Yeah. What does it say for the course code for this one? Oh, okay. Yeah. Yeah. Yes, one of my North Bay students just mentioned something that, yeah, this course kind of has two different course codes. MTH 360 is just like the local Canador one, and then they kind of have a more broad one, which is MEC 903, which is the code for the course for all the colleges. So yeah, they're both pretty much. Oh, and someone's just asking about their second class today. So yeah. Oh, okay. Yeah, I have no idea. I can't answer that question. I have another class after this, but it's a pre-health class. Okay, so hectic day, lots to figure out. I guess it could be worse. At least everyone hopped onto Zoom and stuff like that. Um, okay. So does anyone online have any questions? Anyone here have any questions? At least we kind of figured out the bright space thing. Okay, so I think we're almost done. It's almost 11:30 anyways. So I think we'll conclude with that. So everyone, try to get your bearings. Hopefully everyone has a copy of the textbook or access to it. Check out those review sections if you want. So I'll stick around for another minute. Otherwise, everyone can hop off and have a good day, and I'll see you on Thursday. And if anyone has any more questions, again, I'll be around for another minute. Otherwise, thanks for coming, everyone, and have a good day.